the very first day of the course, I talked to you about a hypothetical 3-address computer. And that computer used sort of direct pointers into the big slow memory, if you remember. So, for instance, if I wanted to add 2 numbers that were located in that big slow memory and put the result into a 3rd location in that big slow memory, I just put the pointers in the instruction itself. Do you remember that? That was kind of this hypothetical machine which we discarded very, very quickly, but one that didn't have a register file at all. And instead of doing things this way, we decided that this was bad because if that big slow memory was very big, the width of those pointers into the big slow memory would be very, very wide. It would be very large. And as it turns out, we also discussed that big slow memories have a problem in that they are slow. It's fine that they're big, but we want them to be fast. We want our computer to run fast, not to run slowly. And so an ideal memory system might be characterized by this gigantic bunny over here. But the truth of the matter is that memory systems consisted of either small, fast memories or big, slow ones. And so as a result of this, well, let's say, actually before that, we talked a little bit about why it was that small memories were fast and big memories were slow. And first of all, even before we talk about why, I didn't show this before, but last night I spent some time on the web and I looked up present-day data in terms of prices and sizes and things like that. And so we have the whole gamut here from tape memory systems, which tend to be the biggest that there are, to disk systems, to what is typically the DRAM inside of a machine, which you typically have 64 or 128 megabytes of, to this new kind of memory which we're going to talk about today called SRAM. S stands for static, and that's the kind of memory that's actually used for the register file and also used for the caches inside of the machine. And what you discover is that the memory of different forms comes in different prices. And I've normalized the price here per megabyte. And so we have $1 milli dollar, a tenth of a cent per megabyte. This is an amazing one because this actually used to be 0.1 only 2 years ago. And now it's 0.004. So this number keeps on going down, but it's not quite at the tape level here yet. But 0.004 of a buck per megabyte for disk, $1 per megabyte for DRAM. If you go out on the market and you want to buy a 128 meg DRAM set of chips, it typically costs on the order, not exactly, but about 128 bucks. And then finally, this ridiculously expensive SRAM, static random access memory. And we'll talk about how that works. But the first thing to notice is what the latency of these different systems are like. A tape takes around 100 seconds to access a random place on the tape. Now, why is that? Well, because the tape is all reeled up on one reel, and it has to wind all the way over to the other reel. And on average, the amount of time to get from one place to around halfway down the tape, which is where you're going to need to go to, if on average you're trying to get to a random place on the tape, is around 100 seconds. That is a long, long time. Okay? So tapes typically are not used to implement the register file on a computer because otherwise the computer would be very slow. It wasn't always like this, okay? Back in the old days, sometimes people thought of this, but it really doesn't work too well. What about a disk? Well, disks are much faster, 10 milliseconds. Now that's pretty damn good, okay? 10,000ths of a second, but still ridiculously slow compared to the 1 gigahertz that your processor is going. Now where does this 10 millisecond number come from? 2 places. A disk corresponds to, or consists of a bunch of platters that are spinning around, sort of like a record, in the old days. And they spin around at a certain speed. And on average, you have to wait for the disk to turn around halfway to get to the data that you're looking for. Okay? Then, in addition to that, there are many, many tracks. They're actually called cylinders on the disk drive, and the head has to move back and forth. Again, like in the old days, the needle on a phonograph. I don't know how many of you guys have ever seen that, but to get to the right place on the disk in a radial fashion, okay, and that takes a little bit of time too. It actually turns out that the rotational time is the dominant part of these quote-unquote seek time to get to a given place. Those heads move extremely fast, but still on the order of 10 thousandths of a second. Yeah?
Are you talking about a floppy disk?
No, I'm actually talking about a hard disk. A hard disk. A floppy disk is much more slow than this, but floppy disks are on their way to the graveyard anyway, so I didn't bother to put them up here. So 10 thousandths of a second, a lot better than 100, but still not that great. DRAM, the sort of stuff that you go when you say, I want 128 megabytes in my machine of DRAM, latency time on the order of 60 nanoseconds, 60 billionths of a second. Now, it's important not to get confused between latency and throughput. A lot of you go and you buy these SDRAMs that say that they're 100 megahertz SDRAMs, and you get the idea in your head that they transfer 100 megabytes per second, or even more than that, 100 megawords per second some of the time. That's true, but keep in mind that that DRAM itself is heavily pipelined. It still has a latency to get the first word of 60 nanoseconds. Oh, and they don't talk about that when you buy it, but it's true. Okay. And what that means is that if this were to be used to implement the register file, we'd be in trouble, because our machine is running maybe 60 times faster than this. And that means every time it wants to get a new location in the DRAM, some random new spot in the DRAM that it hasn't accessed before, it has to wait 60 clock cycles in order to get it. Never mind that it clocks out much faster than that once it begins to go. The latency is very long. Finally, we have this ridiculously expensive static random access memory. And this stuff is typically on the actual chip that the processor is on. It's right there with it, and that's why it costs so much, $500 per megabyte, because typically you don't have a megabyte of it on the chip. You usually have a few 100,000 bytes of it on the chip, some fraction of this. And so maybe $50 worth of the chip is devoted to the cache, to the static RAM. And lo and behold, we finally have a memory system that can keep up with the voracious demands of the processor and give a word out every billionth of a second. Okay, and you can make it even faster than this, but this gives you roughly what the order of magnitudes are for these things. Throughput tends to also go from the highest to the lowest as well as you go from SRAM down to tape. But keep in mind that these numbers give you a hint that certainly in the case of tape, 50 megabytes per second, but 100 seconds to get to the first byte. There's this tremendous disparity between these two things. This latency is not 1 over the throughput by any means, right? You have to reel and reel and reel and reel and reel the tape till you finally get to the beginning of the stuff you want to get. But once you're there, you can read stuff at a very high rate because it's packed in very densely on the tape. Okay, so this kind of trade-off happens all the time. There are some physical reasons for the trade-off, and we hinted at those at the beginning of the first lecture of the course. The first has to do with something that you understand very well now. This is a picture, if you recall, of a DRAM. Each one of the capacitors here is storing a little bit of charge, and these are the transistors that are used to connect that capacitor to one of these sense lines that goes over here. And this is a row select line that's choosing the whole row. But if I were to try to shrink this chip down and make these capacitors very, very small, as I shrink them and shrink them and shrink them, what happens? The amount of energy that they store goes down. And as the amount of energy that I store per bit goes down, when I do the sensing, what I need to determine is the energy above a threshold or below a certain threshold? And when we studied metastability, we learned that the way that you do sensing of that sort is you use the energy that's stored in this capacitor to begin with, and you put it into a thing called a sense amplifier, which basically uses positive feedback to say if the energy is high, if it's a little bit like this, drive it all the way the rest of the way high and sense that that's a logic high. And if the energy is low, a little bit below the threshold, drive it the rest of the way low and determine that that's a low. Well, as you remember from the metastability stuff, somebody is in a metastable state chewing the pen. The closer we get to the vertical, the smaller the difference between high and low, the longer a given sense amp is going to take to resolve whether it's a high value or a low. And in fact, if you think about it, it turns out that there's a version of Heisenberg's uncertainty principle which talks about energy and time. And it turns out that you can extract actually from the physics of the Heisenberg uncertainty principle the fact that the less energy difference there is in a system that you're trying to decide, did it have more or did it have less, the more time it takes to figure it out. Same way as with votes, as we've joked about here in terms of the politics of this year. Okay? So the denser the memory is, the slower it's going to be. Kind of sucks, but that's the way life is. Okay? There's also other problems as well. First of all, we talked about decoding. Remember I said if I wanted to decode a particular student from this group here, I could build myself a logarithmic tree which branched by a factor of 2 every time until I finally found the student that I wanted. Another way of saying this is, let's say that I have a bunch of bits here that I want to choose one of, right? Well, the way to do that with a sort of scalable amount of hardware is to build a decoding tree like this. And whoops, we've run out of one here, right? But we'll just pretend that there's more. And you build a tree like this. If you have n elements here, the depth of this tree is going to be log n. And so you know that as the number of elements that I need to choose from grows, the depth of this tree is going to grow too with order log n depth. And so that tells you that the speed of the memory system, the latency of trying to get to a particular bit here, is bound by having to be less than log n as n gets deep. But it turns out that there's a worse limit that's even worse than log n, and it's one that's the cube root of n. And what that says is that these bits have to exist somehow in the real world. If I have more and more and more bits, I need to pack them into physical space. And in particular, physical space is 3-dimensional. And in order to get to a particular place in 3 dimensions in terms of the speed of light, as the size of the memory grows, we're ultimately limited by the distance the bit needs to travel in order to get to us. So fundamentally, as the number of bits gets really, really big, and the memory system grows more and more and more and more, you're limited in physics by the cube root of n. And so if I were to plot sort of latency, let's see how I should do this, number of bits and latency here, at the beginning I'm going to have a curve which sort of looks like log n, okay? But then later on, what does the cube root look like? Is it steeper than log n? Is it flatter than log n? Or does it go up more than log n? Steeper. So it looks steeper, right? So there's another thing here, and this is cube root of n. Okay? But the important thing is as the number of bits goes up, the latency goes up. And there's a fundamental reason why that needs to be true.
You want the 3 on the outside of the radical.
I want the 3 on the outside of the cube. Oh,
It's not
it's not n
n times
times the cube root of 3. Whoops. That's exactly what I meant to do, but didn't do. Thank you. Okay, so there's the 3-dimensional nature of the world. There's trying to access log bits. All of these things work against us as we try to make memories big. Okay, now what did we do in that first lecture? We decided that we're going to fake a big fast memory by combining the big slow memory with a small fast one. And the small fast one was called the register file, right? And we explicitly managed the caching of data items from the big slow memory into the small fast one by using load and store. We said, you know, I'm going to have this small little cache, which is the register file, R0 through R30. Remember, there's R31 here, which is all zeros. But that will be a cache. And what does that mean? Like a cache of weapons, a cache of food, right? We're going to have a small little reserve where we're going to keep things, where we're going to store things. And then we'll have this gigantic slow memory out here. And we will move data back and forth from one to the other with load and store. Load will be used to do that. Store will be used to do that. And all of our operations will be done within the cache. Okay, it was an explicitly controlled cache. And so, having decided on that, we were happy. Why? Because loads and stores were infrequent, and we saw that we could do most of our programming in terms of getting the values out of this small, fast memory, and only occasionally did we have to suffer the time delay to go to the big, slow one. And you saw in the lecture on pipelining that the problem is that loads were very slow. Okay, we had to watch out because if we did loads too often, this machine would have to stall waiting for the data to come here. Why did this work? It worked, if you remember, because of locality. The idea that you tend to access the same locations over and over again in time, and that was called temporal locality. And if you accessed a particular location, then chances were high that you were going to access locations that were nearby, and that was called spatial locality. And so if you remember, this was a picture of what the code and the stack and the data might look like if we did a time trace of accesses to that big, slow memory. Now, another way of thinking about why this works is if I consider the locations that are accessed in a memory system, what I can say, now that you guys have understood some of the stuff in the physics of these things, in particular in information, is that the record of which addresses are accessed has low information content. In other words, there's a lot of redundancy there. I can predict, if I look at this picture over here, if I've had an access here, then I can predict that the next access will probably be close to here and unlikely to be here. And so when I get this new address, this new piece of information here, it's not telling me very much. Okay? In other words, I can use the past to predict the future. If you've just borrowed a book from the library on plumbing, chances are you will borrow another book on plumbing. If you, well, that's if you're a Republican back in the 1970s. No, that's and you need to learn what kind of suit you should wear when you every chance I get. Using the past to predict the future is what low information is all about, okay? When I say I'm tossing a crooked coin and I say the average information content is low, it means that I can use the fact that there have been more heads than tails in the past to predict that probably there will be more heads in the future, okay? And so saying that I can predict the future is another way of saying that the data stream has low information content. The highest information content came from a random data stream, in which case the past doesn't tell you anything about the future, where every coin toss is an individual random event. So we're beginning to get kind of the linkage between the past and the future, information content, and this idea of locality. What we're going to do is we're going to decide that this breakup of the system between the register file and this big, slow main memory is one step in that direction of trying to create the illusion of a big, fast memory, but it's not good enough. It is still the case that whenever you try to do a load from main memory, the machine has to basically stall for a long time. In the example that I showed on the board, if the main memory has a latency of 60 nanoseconds and the machine is running at a clock period of 1 nanosecond, that's 60 clock cycles we have to wait, which is a long time. So we're going to insert in between the two things another stage of intermediate size, pulling basically the same trick as before, and loads and stores are going to be filtered through here. And this thing over here is going to be called the cache. And what's neat about the cache is that to the computer, to the programmer, we're going to make the system work in such a way that the cache is going to be called what's called transparent. In other words, if I were to suddenly get rid of it, the program would still run. It's very different than when we created the register file, because the register file needed these explicit instructions to move things back and forth between big and small storage. Okay? This will operate automatically. Okay? And what's going to happen is that if I load a data item from here, it's going to make a copy. Say there's a fish here, make a copy over here, so that if I ask for the data item again, instead of having to incur the 60 nanoseconds of latency going into here, it'll get it from here. And this, as you recall, is much faster. Okay? It may even be the case that if I load a data item from here, and there's another one that's sitting right next door, that I'll load both of them into here, only pass the first one on, and then if I need the second one later on, I won't have to, again, incur the 60 nanoseconds to access the slow memory here, but rather I'll get it directly from the cache. Okay? So this is sort of an extra level that we're adding here into this multi-level memory system. Okay, how's it going to work? Well, we're going to keep what in Scheme you learned was an association list of addresses and values. So, every time that I read a particular location, I am not, when I do a load, okay, I am not going to automatically go to the main memory for it. What I'll do instead, I'll search the cache saying, is it in the cache? And if the answer is yes, I'll call that I've got a cache hit, and I will return the data from the cache. And I won't bother to wait for those 60 billionths of a second to get it from the main memory. If it's not in the cache, I'm going to say, whoops, it's a cache miss. It wasn't there. So I've got to trundle off and go to the main memory, wait the 60 billionths of a second, and when I do finally get it back, I will put a copy of it in the cache. Why? Because locality says if I used it now, if I ask for it now, chances are I'll ask for it again very soon. The cache itself is going to consist of two columns of stuff, one being the address of each data item, and the other one being the data item itself that would be found at that address in the main memory. Yeah?
According to the principle of locality, do we store just the recently used data or also some of its neighbors?
Well, we have a choice, okay? And spatial locality would have us go ahead and store some of the neighbors as well. And we'll talk about that in a few seconds. We have to be careful, though, not to get too excited about this, because when we store the neighbors of a data item, what might happen? We might not really want them, right? And furthermore, the idea of what's a neighbor and what's not, right? Like what would be near plumbing that we might not want? Plums, right? Okay. So, no, this is actually a big thing, okay? So let's say that you go to the bookshelf in the library. Okay, here's the Boston Public Library, okay, BPL, okay? And you go here and you get the books on plumbing, and that's this here. And, well, of course, that's not really how it's organized in the library. I know that, okay? There's a Dewey Decimal System and da-da-da. But let's say that we're in this fantasy land here, okay? And right next to plumbing is plums, okay? Well, if we decide that we want a block that's this big, and we get plums also, we may spend a lot of our cache and waste our space in our cache bringing in plums, which we'll never look at. Because after all, you know, we're kind of from the right wing, and we don't really, men don't cook when they're, you know, when they're Republicans, right? You know, so we don't want the plums. Okay. Anyway, we're going to see how exactly issues like this determine how big of a chunk we actually want to get out of the main memory at any given time. Yeah.
Do software developers for any particular program have any kind of control over what kind of cache might be used, so that they could decide for our program we would want spatial, we wouldn't want temporal?
Absolutely right. So let's say that we had a program that talked about how to build a machine to process plums, okay, and it wanted plumbing and plums at the same time. Could we give a hint to the cache saying use a bigger block size? Things like that. In general, the kinds of processors that are out there, that's not true. Okay, there are some experimental ones that are in labs that do allow the program itself to guide the cache just a little bit and to say, I do want to keep a hold of this, I don't want to keep a hold of that. But state of the art right now is no. But there are experimental machines for which that is true. Keep in mind that the register file is a form of that. It's a form of saying, I want to keep the following things in the register file. and the program has complete control over this very small cache here. And there have been some machines where this doesn't exist, but the register file is bigger, okay, is several thousand words long, and the program explicitly controls this thing here. And there have even been some systems built where this does not exist, but there's only the automatic cache. Okay, but in general, no. This is an automatic thing that you can neither sense is there, nor can you tell it what to do. Okay, yeah.
Is the video memory entirely separate from the system?
The video memory. The video memory is a peripheral that's sitting off to the side here. So here's the processor, typically called the central processing unit, okay? And it doesn't matter how it's hooked up, but you can think of it as a separate thing where there's a memory here for video where the processor gets to draw things on the screen. In some systems, the IBM PC is unfortunately one of them, okay? This video sits over here, and some of it goes through the cache, okay? The same cache that's used for other stuff too. And if you look at the BIOS when you start up your system and you press setup and things like that, you can really mess things up this way. So don't do this at home. But you can often turn on and off caching of the video memory system. But it's in fact a separate memory system from the main memory of the system. And actually on the PC, you only get a window into the memory, and you constantly have to move the window back and forth, which is a whole nother thing. But in general, this is a bad thing to do, okay? And if you're going to cache things here, there should be a separate cache for the memory system.
Is VRAM intrinsically different from SDRAM?
It is, and the reason is that on the other side of here is a screen, and the way that the screen works is that the screen forgets all the time, okay? So there's a beam that scans over and over and over and over here, and then when it's done with one scan in 1/60th of a second or a little less than that, it goes back and it has to start all over. So constantly there's a stream of read requests coming into the VRAM here and data flowing back here. Incredibly high rate data going on this side. And then on the other side, there's reads and writes that are going in from the processor, typically at a much lower rate, okay? And so VRAM is specialized to allow the right-hand port to do that all the time and the left-hand port to do it less of the time, whereas this is sort of a single-ported system here. Okay, so you get a little bit of an idea of what the cache might be like. Now, how does the cache make things faster? Some of the time you get a cache hit, and that's good, because you don't have to go all the way to the slow memory. And some of the time you get a cache miss, and that sucks because it means you have to incur the long time. Well, there's a very straightforward formula where you say basically the hit ratio, what fraction of the time, where 1 means all of the time, do you get a hit? And 1 minus alpha is the miss ratio. What fraction of the time do you get a miss? And you can gather statistics on how often you get a cache hit versus how often you get a cache miss. And if the access time of the cache is T sub C, and the access time of the main memory is T sub M, then all you do in order to find out what is the average access time of the computer for doing a load or a store, it's just the weighted average of the two. Because when you have a cache hit, you incur the time T sub C, so it's alpha times that. And when you have a cache miss, which is 1 minus alpha of the time, you have this cache miss T sub M, and that's how long it takes to go to the main memory. Now, this is for a circumstance which is called a parallel search. What that means is that the computer, when it does a load, searches the cache and the memory at the same time. So let's say that it's searching for location 100. It will start a read from location 100, and it'll search through the cache for a table entry whose address tag says, I have the data for location 100 in here, looking for the data, and whichever one gets it first, it will abort the other one. In particular, if it gets a hit here, it'll stop doing the memory lookup here and then go on to the next thing. Okay, and that means that reads, when they hit, only take this length of time, and when they miss, they only take that length of time. But in fact, if you think about it, a simpler system would be a sequential search. That when you do a read, you first look for it in the cache, and then if you don't find it, you look for it in the main memory. And that means that when you get a miss, how much time does it take? the time to look it up here in the cache, plus the time to look it up in the main memory. And so that's why if you do a serial or a sequential search, the formula is a little bit different. During the time when you have a cache miss, it's 1 minus alpha t sub m, but whether you have a hit or a miss, you always have the time t sub cache. So you don't multiply this by alpha. Now the truth is that the two formulas here, whether you do the search in parallel or in sequence, in fact doesn't make that much of a difference. And the reason is that guess how high alpha typically is? Guess how much?
Ben told us 50.
What did he say? Oh,
96%.
stole my thunder, 96%, which is an amazing thing, okay? Because when I first learned about that, I said, wow, it can't possibly be true. Because after all, this cache is small, and the memory is big. What if this is 128 megabytes, okay, and this is 128 kilobytes? You know, that's a factor of 1,000 different. That means that 1,000 times more locations in here are competing for, or excuse me, let me say this the right way. 1,000 locations in here are competing for every spot in here. And yet still, we find what we want in here 90-some-odd% of the time, which is amazingly good. Okay, and that means that the proportion of misses is not so bad. On the other hand, when we do have a miss, the cost is very high. The cost may be 60 times higher to go here than it is to go here. So again, in figuring out the average time, it's a small fraction of the time that we're going here, but a lot of penalty. Okay? The idea is that the cache is a runtime mechanism that is figuring out at runtime how things go, and supposedly the design is so good that regardless of how things go, it will improve the performance of the system very well. The truth of the matter is that if you give me a strategy that the cache is using to figure out which of every of the 1,000 things it's going to put in here, I can write a program for you that will mess that up and that the performance will be awful. Okay? So in truth, it helps if the compiler writer in fact does know, but the people who design caches will tell you that that's not true. Okay? So it's kind of coming from both sides. And again, the experimental machines are trying very hard now to figure out some ways for the program to give hints to the cache saying this stuff matters more. But in a few seconds, we'll talk about how certain things matter more and how it keeps track of that. Other questions?
Yeah. Is the cache size that's required to make the computer run effectively dependent on the architecture or the speed of the CPU more, or is there some other factor that decides? I mean,
yeah.
older CPUs probably only had a 32K cache.
Right. Well,
years ago,
okay. So,
500K.
in fact, there are many things that make a difference. Let's ask the question a different way. How high should the hit rate be? Okay. It's obvious, I think, to everybody here that if I make the cache smaller, the hit rate will not be as high. Certainly, if I make it 0, it will not be high at all. Okay. It'll be 0. And thus, the only advantage of making the cache bigger is that the hit rate goes up. But why does the hit rate need to be higher? Because of the disparity between how fast this is versus how fast that is. Okay? Again, it's how much of a penalty do we get by having to go to the main memory. And the problem in modern times has been that this processor here is a monster. Okay? It's running 1.5 gigahertz. Okay? Just tearing through data. It has this voracious appetite. I want more data. Give me more data, okay? More input, as Johnny Five used to say, the robot. This is leading into Friday's lecture. More input, okay? That's what it's saying right here. More input. More, okay? I want more. This isn't Moore's law. That's a totally different thing. It's sort of the same, actually. Where's it going to get it from? If this memory is so damn slow, there's only one way to fix the problem. And that's to get the hit rate on this cache up higher, okay? So that we don't have to stall waiting for the main memory. And that's the reason that these caches have gotten bigger and bigger. It's just because this has gotten so damn fast versus the speed of this thing.
But the larger the cache, the slower it would get.
It gets a little slower, but not much slower. So this curve that I drew you here, I guess I should say that, you know, this is as the number of bits gets very, very big. Okay, down here, we're in a region of technology where every few years the systems get faster and faster and faster. So this constant factor that keeps pushing down that curve keeps getting better every year. So memories typically these days are bigger than they used to be and faster than they used to be. That doesn't mean that curve's wrong. Okay, if you were to stop the clock and say using technology of December 2000, how slow is a memory versus its size, that curve still holds. Okay, but the trouble is that if you let people innovate, then the constants change. And so as time goes on, the memories get bigger and faster at the same time. Yeah.
Now, most machines now have 2 levels of this cache for.
You bet. So I wasn't going to talk about that till the end, but in fact, they go even further, and they have the level 1 cache and the level 2 cache. And so it's like this big cone here as we keep getting bigger and bigger, and this one is faster still. And it, again, at any given time, it obeys that curve. Okay, so this one's faster than this one, which is faster than that one. And you sort of are kind of matching, and that's slower than this thing, which is the smallest one of all, but the fastest of all. Okay, which is the register file. So, yeah.
The cache is faster purely because they're smaller and there's less to sift through? I mean, they're the same.
There's actually two.
They're the same type of RAM?
No. There are 2 reasons. One is that they have less total bits. 2 is that the size of the bit on the chip is bigger. There's more energy per bit. Okay, and remember that the less energy per bit, the slower, the longer it takes to figure out was it a 0 or was it a 1. So in the register file and in the caches, we tend to use what's called a static RAM cell, which has a lot of energy per bit. And when it's time to sense whether it's a 0 or a 1, bang, we know the answer, because it's a lot of charge.
So it's more like the register SRAM?
It's exactly like the register SRAM. Yeah. Lots and lots of registers. Okay.
What's the ratio?
But,
Sorry.
oh, no. Well, the last thing that I was going to say is that typically the boundary of the integrated circuit, so the processor is on an integrated circuit, the register files are on the same chip, and then either the L1 cache is on the same chip and the L2 cache is not, or for newest chips, both of them are, and the boundary of the chip is there. And it turns out that physically, as soon as you get off of the chip, the one chip that's going to hold all this stuff, and go to a set of wires to another chip, everything slows down a great deal, because you need to drive those wires. Yeah?
Stepping from register to cache 1 to cache 2 to main memory, what's the ratio of the sizes?
Well, I can give you typical numbers. So this over here was on the order of 32 words, okay, which in this case of our machine was 64 bytes. Sorry, 128 bytes, thank you. 128 bytes, okay. This is 128,000. Something in here may be on the order of 2,000, 2K bytes, something like that. Okay. But each time kind of going up by a factor of 100, factor of 1,000, something like that. And tomorrow we're going to go from here to gigabytes. We're actually going to add one more step to the end here. We're going to put a disk here, which is really slow, as you saw. And we're going to show how to make the system act as if the memory is not this thing, but is the big disk here. We'll talk about that.
Repeat those numbers
Yeah.
I missed them for the level 1 and level 2 cache.
I am just guessing here, but this is on the order of kilobytes. This is on the order of hundreds of kilobytes. This is on the order of hundreds of megabytes. So, and this is on the order of hundreds of bytes. It changes every few months, okay? So it's like,
Yeah.
you know. Okay. How do we actually build this cache? Well, we said we're going to have this association list between an address tag and the data that's associated with that address. And the first thing we might think of doing is what's called a fully associative cache. And here the idea is that we simply have a bunch of storage locations that have pairs in them. And the left element of the pair is the address tag. And we compare the address that we want to see, is this in the cache, with the tag that's being stored here. And if they're equal, aha, we got a cache hit. And so we enable, this is actually a type of gate that's, you guys haven't seen it here, but it looks like a buffer, but it has a wire that goes into it on the side that says go ahead and allow the data here to pass out to over here. You can think of all of these. Sorry? You can think of it just like a switch. You can think of all of these triangles here as a giant selector for choosing which of the inputs here gets to go out. Okay? Except the controls for it are the individual ones on each one of these gates here. Okay? And so there's a big OR gate, which I haven't shown here, but if any of the equal signs fire, we get a hit. And whichever one fires steers its data to the output lines, and that's the data out that comes out there. Now, this kind of memory is called a content addressable memory, or a CAM. Why? Because unlike a typical address selected memory, we are not saying which of the rows we want to pull the data from, but rather which of the tags we want to match in order to pull the data from. And we're letting the memory itself figure out which row has the match. Okay. And this is a really great cache. What's nice about this kind of cache is that any particular address in the slow memory can be cached in any of the locations inside of here. There's no constraint in any way saying that address 100 needs to be in this row. It could be in this row or that row or the other row. It really doesn't care. We haven't talked about how it figures out what to cache and what to throw out and stuff like that yet, but we will get to that. Now, sort of a polar opposite to the fully associative cache is what's called a direct map cache. And in here, there is an absolute constraint on where every piece of data is going to go in the cache. And in particular, what we're going to do is we're going to take the incoming address and we're going to hash it. Now, you guys did hash functions, yes or no? You mentioned hash functions. Okay. A hash function is a way of taking an input data value, which can range anywhere from a low number all the way up to a very big number, and putting it through a hash function h that compresses it into a smaller range. So from 0 to big N all the way from 0 to small n. And so basically, it does that. And a good hash function will mix up the data at the same time so that if I have a piece of data here, now what does that mean? This is a many-to-one mapping, right? Which means that this location here and let's say this location over here are both going to map to the same number on the output. Okay, it has to be true, right? You can't take a range that's big and squeeze it into a range that's small without that happening. Okay? So the hash function that we're going to be using, because this is the range of memory addresses that are in the big memory, and this is the range that's in the cache, which is a much smaller range, we're going to establish a direct map between every one of these and every one of those, and we will know beforehand that this is a many-to-one mapping. And so in this case here, where this is 1,000 times bigger than this is, there will be 1,000 locations in the main memory which will hash to the same location in the cache. And what function are we going to use? Well, we're going to use this one. We're going to take the low-order address bits of the incoming address. In other words, if something is meant to go into a particular location in the main memory, we're going to divide the address of where it's supposed to go in the main memory into two sections, low-order bits and high-order bits. And we'll only use the low-order bits to select where in the cache it's going to go. And what that means is that two addresses in the main memory that have the same low-order bits will hash to the same place in the cache.
How many bits are you using?
Well, it's up to us. Okay, so for instance, if we have 128 kilobytes in there, let's say there's 128, let's for a moment here say that's 128 kilobytes is going to be divided by 4 is 32 mega words. And let's make this thing 32K words. So how many words do we have in the cache? 32K, which is 2 to the 10th times what? 2 to the, what's 32? 2 to the 5, right? I think that's right. 2 to the 4 is 16, 2 to the 5. So that's equal to 2 to the 15. So we're using 15 bits. That's how many rows there are in the cache. So we're going to choose K being 15 bits, and we're going to take the low order 15 bits of the addresses that we use for loads and stores, and we're going to use them to determine which location in the cache we're going to use. Okay. Now, with 15 bits going in like that, all of the other bits are the high order bits, and it's possible that many different addresses that have the same low order bits will map to the same place in the cache. And we're going to need to be able to know where this particular one came from. So in this tag over here, we are going to store the high order bits that correspond to where the data came from. And when we do a read, we will compare that tag with the high order bits of what we're looking for, and if they match, we'll say we have a cache hit. Now notice that this system is more simple than the one before. We only have one comparator down at the bottom as opposed to one for every row, because we're only going to be comparing one row for every given lookup in the cache. An address comes in, gets split in half, right? The low order bits are used to choose a row, because if that particular place in main memory is cached, then it's going to be in that particular row. We then compare the tag for that row against the high order bits that we're trying to look for, and if they agree, then that is in fact the data that we want. And then this data here is the data out, and we get a cache hit. Now when we put something in the cache, we will write into this tag field the high order bits that correspond to the location where we got the data from in the main memory.
But there may be 6 or 7 messages in the same location.
And so we will be forced to overwrite all of them except for the last one. We cannot store more than one piece of data from any location that has the same low order bits in this system. Okay? So this cache is much more simple than the other one. Now why is it that taking the low order bits is a good idea? Well, low order, let's say that I was a little Martian, right? And I was sitting here watching the load and the stores and looking at the bits that come out saying how far into the memory I want to go. And you remember the locality picture. Let me actually go back to there. Oh, there. Which bits in the address lines coming out of the processor doing loads and stores, which bits do you think changed the fastest? Which ones are changing all the time versus which ones are changing the slowest? The low order ones are changing fastest. Why is that? Because the low order ones typically, not all the time, but as we do this counting up like this, as we locally go up and down, it's the low order bits that are changing. Right? If you take your car and you drive back and forth on the street but don't go very far, the odometer, it's the low order bits that are changing the most. And the high order ones only change if you go from here to some other state. Okay? And so as a result, we can depend on those low order bits spreading the data around in the cache. In other words, we will not get what's called a collision between data that we want to store at any given time in the cache. The data that we want to store will typically be spread out in its low order bits. So that's why we use them. Okay? Any piece of data from any place in the main memory can be in any row.
Well, but when you then try to find it, it seems you have 100.
Then in parallel, we need to check them all. And there's a lot of hardware, right? Every word in the cache needs this equal sign thing. And those searches, all 128,000 of them, must operate, or excuse me, 32,000 of them must operate in parallel.
So you're saying the lookup doesn't take longer?
Well, it may actually take longer. This cache costs a lot of money. It's very hard to build one of these. Okay? On the other hand, this one doesn't cost a lot of money because there's only one of these guys, and we know exactly from where to get something. But this cache can suffer from collisions. What if it just so happened, again, going back to our picture, what if it just so happened that the low order bits that we're using down here are the same as the low order bits that over here? It's not likely, but it might happen. Or maybe those are the same as the low order bits that are here. Then as we simultaneously are accessing data from 3 regions of the memory, the low order bits may cause the same parts of the cache to be competed for. And then we'll have a collision in the cache, and a lot of the data that we want to store in there will have to be thrown out, while at the same time other parts of the cache are underutilized. And so the direct map one is less expensive, more straightforward, and easy to make because there's only one of these things, but on the other hand, it's not as high performance as the other one. It can suffer from these collisions. So what in fact, sorry,
Is the hash function just stripping off the higher order bits?
in the case of caches, that's all that it is. Now, hash functions can be fancier than that, but this hash function is just trying to strip off the lower order bits.
You could make a rough calculation. It seems as though the direct mapping thing you'd still come out on average ahead if you assumed absolutely distributed data, because
It is usually the case that the direct map one, oh, that you come out ahead?
well, because your chance of a hit or the 15-bit K is your chance of a data collision is assuming completely equal distribution is
Right.
1 over 2 to the 15, and your
Ah.
penalty would only be 60.
But the trouble is that the distribution isn't equal.
Right.
Because of the locality of the system,
Right.
it tends to be the case that things cluster a lot. And if you're lucky, the clusters are separate. And if you're unlucky, the clusters are right on top of each other. And then everything's horrible. And so to try to improve this, to kind of go halfway between the direct map cache and the fully associative cache, there's a type of cache which is the universal type that's used these days called a set associative cache. And here's how it works. We take a bunch of direct map caches, 1, 2, 3 in this case, but you may have more, okay? And we run them in parallel, and a given address still has the low order bits stripped, and that determines which row we're going to use. But in that row, the data can reside in n different places, where n is typically a number like 4 or 8, a small number. So this particular one would be a 3-way set associative cache. It's not fully associative. It's not the case that any piece of data from any address in the main memory can reside anywhere in this cache. It's still the case that the low order bits constrain a particular piece of data to reside in only one row, but there's complete freedom into which column, which of these banks of the n ways, which of the ways it can live in. And so if we have 3 areas of activity that happen to have low order bits that overlap with each other, this architecture can accommodate it. So for instance, the stack could use this one here, the program counter could use one here, and something else could use one here. Okay. And so it's associative this way, and of course you can see the fully associative cache is just if we reduce this to 1, right, then the number of bits that we're stripping off is 0, and the full associativity is happening in the horizontal axis here. If we reduce this to 1, then it becomes a direct map cache, and the size of the cache is in the vertical axis. So it's direct map this way, and it's associative this way. And this is just a compromise between the 2 extremes of either the fully direct map cache or the fully associative cache that you saw before. But this is typically what's done. We have n different ways. We have n comparators which are running in parallel with each other. The constraint as to which row we're going to choose, we run the n comparators at the same time. And if any of them hit, then the data goes out and says that everything's good. We've got it in the cache. Okay. We need to figure out for every kind of associative cache, whether it's set associative or fully associative, what's called a replacement strategy. Let me go back here. Let's say that I decide that I have a cache miss, and I'm in the 3rd row. Okay? I have to choose, when I read the data in from main memory, which of these ways I'm going to put the data in. Should I put it in this one? Should I put it in this one? Or should I put it in this one here? And let's say that this cache has been in operation for a long time, meaning that all of these things are full. The cache is all full. What it really comes down to is which thing should I throw out? What should I replace in the cache? And I have a choice of one of 3 things. What should I do? Well, somebody at the beginning of class said, well, maybe we should throw out the oldest one that's in the cache. Because after all, if locality is the case, the thing to get rid of probably is the oldest thing. And that way, my chance of using the other things is greater because they are more recent. And that scheme in particular is called least recently used. Okay, so that's one replacement strategy, LRU, which says I will throw out of the cache the item that is least recently used. Now in the direct map cache, I have no choice. I have to throw out the one that's there because there's only one place for me to go. But for fully associative and set associative, I do have some choice, and so I can keep track of the least recently used. Another generic way of doing this for throwing things out is called first in, first out. So that's not the least recently used, it's the least recently that was brought in. So I get rid of the one that came into the cache the longest time in the past. Okay. Again, the assumption is that things that I bring in more recently or that I access more recently, that I use more recently, are in fact more likely to be used again in the future. Another choice, random. I just pick one at random and throw it out. Guess how badly that works? Not badly at all. Okay? It turns out that if you just randomly choose one, say you're it, bang, and then bring a new one in and replace the old data, that works pretty well too. And so you will find some caches use a random replacement strategy. And then finally, there's some of the things that people have been doing some hints at where the program itself can help guide which thing in the cache should be thrown out. And in particular, some research computers and research programming languages allow you to specify that this variable that you're using at any given time is one that you're going to use a lot, so please keep it in the cache. And they help to guide what the replacement strategy is. There are other bits in the cache that we're going to use as well. In particular, there are typically valid bits, which are marked in the column here V. And what they say is whether or not the item in the cache is any good. Okay? And when you first turn on the computer, all the valid bits are set to 0, and then after a while, when things are read into the cache, the valid bits are set to 1. And so you don't pay attention to the data. You don't say you have a cache hit unless the valid bit is a 1 and the tag matches the address that you're trying to bring in. Occasionally, a program may want to say, I'm all done with everything in the cache, so flush it out. And what that means is it will set all the valid bits to 0. Let's talk a little bit about multiple processors, which is a thing that is happening these days quite a bit. So let's say we had a bunch of processors, and we had a main memory that was down here, and we had some kind of bus for hooking all the processors up to the memory. Part of the problem with an architecture like this is that the processors have to compete for access to the memory through this bus. This becomes a bottleneck. And so what is typically done is that the caches are put in front of the bus between the processor and the bus. And that means that most of the accesses, the hit rate, will come from here, and you won't have to go out to the bus. And only when you get a cache miss do you go out down to here. Okay? Sounds like a great answer, except for one thing. What if this guy is caching the same data item that this guy over here is? And what if this one decides to do a store and writes the data value right here? Will the copy of it over here necessarily be updated? What's the answer? No. Okay. So we need what's called a cache coherence policy in order to make sure that all the caches stay synchronized with each other. And in particular, if this processor wants to write something that the other processor over here is going to read, we need a way to do that. And there are many, many different ways to do this kind of cache coherence. And I'm only going to talk about one of them right now. One of them that is the easiest to do is what's called a system where we write through the cache. Instead of storing things in the cache when we do a store, what we'll do is whenever we store anything into the cache, we will also store it into the main memory of the system. And this other cache, and this one here, will be what's called a Snoopy cache. And it will listen on the back channel over here whenever it observes a store going on. If it happens to have the same value in its cache, it will either update the value in its cache, or if that's too hard to do, it will just mark it as invalid. And once it's done that, if this guy asks for it again, it'll get a cache miss, and it'll get the newest version of it from here to go back. It's one of many, many different ways to do cache coherence. And so this gets us into what the write policy is, what the store policy is going through the cache. Now, one of the neat things which you probably notice when writing programs for the beta is that there tends to be a lot more loads than there are stores. Typically, the ratio is around 4 to 1, okay? And so it's okay if writes are slower than reads, if stores are slower than loads. And so what we can do is we can use a policy like what I just said called write-through, where writes go to the main memory as well as the cache. There are other policies as well, one where you don't ever write to the main memory, where you never write to the cache, one where you allow the writes to kind of catch up with you afterwards, going from the cache out to the memory, and then the fastest one of all is called write back. And what that means is that when you write something to the cache, it just goes to the cache, but when you replace something in the cache, that's when it transfers it out to the main memory. Okay? But the one that is sort of the easiest in terms of cache coherence to do is called write through. Okay, let's say though that we're doing just a write back cache. What this means is that if I do a store, then I store the new data value in the cache only. Okay? So here's a pi I'm going to store just in here. When I bring something new from the memory into that same space and I decide to replace the pi, I'm going to write it back into the main memory. Okay, that's write back. Now, in order to try to speed this process up, some of the techniques that are used are what's called the dirty bit in the cache. And so this is yet another column. We already talked about the valid column in the cache. Now we're going to talk about the dirty bits. What a dirty bit means is that the item in the cache is different than the item in the main memory. In other words, it has been written after it was first read from the cache. So if I do a load from one location in the memory into the cache, the dirty bit is 0. If I then do a store and write that location in the cache, the dirty bit gets set to 1. If later on I read another location in the cache, in the memory, which replaces this item that I have updated here, I need to write this back to here before I bring the new one in. And so I check, is the dirty bit 1? If the answer is yes, I go ahead and I write it back before I bring this in. But what if I check this and the dirty bit was 0? What would that mean? That this value is the same as that one, so do I need to bother to write it back? No, and I save myself half of the time. And just remember that access to this thing is very, very slow. So the dirty bits can save us on those things that were brought into the cache that are then replaced, but which were not ever written, so we can just throw them out because the old value is still here. Okay, that's what the dirty bits are for. Finally, questions about plumbing and plums. Okay. Often because of spatial locality, when we bring in one item from the cache, we want to bring in the items that are near it. And the way that this is done in cache systems is that associated, again, with a particular tag and the valid bit and the dirty bit are not one word of data, but more than one word of data, several words. And what it means is that here is the data at address A. Here's the data at the next place and the next place and the next place, however many large the block is. And typically, this block can be anywhere from 2 words up to usually less than 100 words, but a fairly large block. And in general, it means that whenever we bring anything into the cache, we bring in things that are near it, because we bring in the whole block. The difficulty is that we will occasionally bring in fetches from the memory system that we will not use. We will occasionally bring in plums when all we wanted was plumbing. And that means that you don't want the block size to be too big. Because after all, if the cache is limited in size, you don't want to store things in here that you're never going to use. On the other hand, we know that memory systems have much higher throughput then you would guess by their latency. In other words, the latency is 60 nanoseconds, but the throughput is one item every 10 nanoseconds. And what that means is that you have to wait for 60 for it to get started, but once it starts, it can give you the next one and the next one and the next one and the next one very fast. So reading a block of data from the main memory is not as expensive as if I tried to read that block one at a time, kind of at random, one word at a time. And so the cost to bringing in a block in time is not as bad as you would guess. So again, we're weighing how long it's going to take to bring in the extra words. We're weighing how much storage we're wasting by perhaps bringing in words that we don't need. And there's this trade-off where you find just the perfect block size which optimizes the performance of the system as a whole, where you're in general bringing in words that you will probably use, although it's likely that the ones that are far away from the thing that you're trying to search for are not as likely. So they're reading in words before you ask for them, but they're using the tip-off that you're asking for a word that's nearby. And so they go ahead and they read a whole block. But they never sort of spontaneously say, I bet this guy wants a block near location 2000, so I'm just going to go ahead and read that stuff. On the other hand, there are some experimental research computers and research instruction set architectures that allow you to say, why don't you go ahead and get started reading in things near location 1000, and I'm going to do a little bit of work here, and then soon I'll need that. So you sort of send a messenger off to get a block of books for you, and at the same time you're busy reading your old books, and then they come in the mail, and right? So
What's predicting branches?
That's a totally separate thing.
That's another matter.
That's a totally separate thing. It has a similar flavor to this, but the idea here is that if you remember, well, in talking about how the cache interacts with the memory for the code of the system, in general, you fetch a block of code, right? The assumption is that if the PC is here, it's going to be very close to there in the future, right? But if you do a branch, that's not necessarily true. If you can predict which way a branch is going to go, then you can help steer the logic that helps to decide which blocks to bring in. And so that's how that works. Okay. In particular, the reason that these memories have such high throughput compared to their latency is because they have a lot of sense amplifiers. When they read a row of bits over here, they read the entire row. And so if I want this bit right here, in fact it reads, in this case, all 128 columns of bits. And if I wanted to, after I got that first one, I can get all the other ones very, very fast, because I don't need to read them again. They've all been sensed at the same time. And that's how DRAMs on the inside manage to have such higher throughput than 1 over their latency. Okay, other issues. Should I have one cache both for the instruction stream and for the data loads and stores that are done? How many people think they should be the same cache, and how many people think they should be different? Same. Different. Yeah. Different usually performs better, okay? Unless for some reason some programs are more data intensive than others. So sometimes you find that this cache is being used more than this cache, or this cache is being used more than that cache. And if that's ever true to a great extent, then usually it would have been better to just have one of them where sort of regardless of which is being used more, the total is available to both. But the reason you want them separate is what? So that you minimize the collisions between the two sides, right? That's absolutely right. And so this is kind of one of these higher order architecture issues, but you see people talk both ways as to whether they should be separate or the same.
If they are separate, are they generally equivalent sizes, or is the data, for example, twice as big?
That's an excellent question. In the machines I've seen, the instruction cache is bigger. And the reason is, again, the machine has a voracious appetite, and it's executing opcodes like crazy, okay? What it's not doing is executing loads and stores on every opcode. And so you typically see that the data cache is smaller than the iCache. Okay.
Would these be of the same design, or would you?
It's typically the same design. Sometimes the number of ways can be different in one versus the other. But that's a very, very difficult issue. So. Then there's the question of should the cache be on chip or should it be off chip? So the design that you see here is a case where we have the level 1 cache on chip and the level 2 cache off chip. And then finally we have the DRAM of the system. And then how about the cache as a method of speed matching between the two different things? Remember, even though you buy your SDRAM that runs at 100 megahertz, your processor is running at a gigahertz, which is 10 times faster, right? So what does that mean? That means that whenever it actually gets a cache miss and has to go out to here, even in terms of throughput, don't worry about the 60 billionths of a second, the 60 clock cycles it takes to get the first data item from the cache. Once they're streaming in, it takes 10 clock cycles to get each one after that. So this is, even in terms of throughput, very slow. And so caches are fantastic devices for matching disparate speeds between the processor, which is running at 1 billionth of a second, and this thing, which even once it's geared up and it's streaming a bunch of words out, does 1 every 10 billionths of a second. Why? Because this guy can go on and do other work while we're waiting for the other words to come in here. For instance, once it's got the first word of a block and it's gotten its hit, the other words of the block can come in the background while this thing hopefully is getting other cache hits and doing other work here. And so we can have in parallel the filling of the cache line from here to there while this thing is going at a much faster rate and getting cache hits in the cache. Of course, if it then gets stuck in a cache miss again, it's got to go back out yet again to get this thing. But now you get an idea why it is that the folks who make processor boards are pushing so hard to get this front side bus to go faster and faster and faster. Because going off chip is just so horrendously bad when the processor is running so fast. So, okay, last slide. What did we learn today? We learned a bunch of stuff, right? You can combine small and fast with big and slow, and you get big and fast. It actually works, and the reason is locality, because the addresses are predictable. The past is used to predict the future. And we can describe that in terms of spatial locality and temporal locality, and the replacement policies themselves are dictated by those characteristics. We talked about coherence a little bit. Okay, this is really a graduate topic in general, but I showed you that there is a problem if you have multiple processors with one cache for each one, all sharing a common bus after the cache hooked up to the memory. And the problem there was what? That if an update happened in one cache and a copy was stored in another one, the copy might be stale compared to the updated one. And what does that mean? Well, when we have to have some sort of coherence policy in order to invalidate the stale copies that are in the other caches. And then finally, there's this thing having to do with block size. Block size is a very important way to improve the performance of the system, in particular because the throughput of these large RAMs is so much higher than 1 over their latencies. Okay, anything else? Other questions?
Was Moore's law specifically to apply to the CPU or the processor or the whole memory?
It actually applies to everything, which is just kind of nuts.
It's not smooth,
It applies to, it's an average, it applies to disks, it applies to chips. Chips is what it was done for, okay? It was actually done for chips. But it seems to apply to disks also.
But you're kind of describing a process where one bit of the engine may be going faster than the average of Moore's law.
Yeah,
and the others are struggling to catch up.
it seems that RAMs are behind, okay? And there's probably a really neat essay on why that's true. Okay, but RAMs seem to be slipping behind in general, and so the amount of caching that we're using is going up. But anyway, Moore's law, for those of you that don't know, say that every year and a half, the performance of a chip roughly doubles. So if you buy anything these days, in 18 months, you'll feel like you're a dummy because it'll be twice as slow as the one that you can buy next. You know? So for the same bucks, which is cool.
Is SRAM progressing at the same rate roughly?
SRAM is roughly happening at Moore's law, right? But DRAM isn't, and It's not exactly clear why. I think that in terms of price, the demand for DRAM has gone way, way up. And it's probably because of Bill Gates more than anything else, okay? Because Microsoft writes huge software,
Be interesting
okay?
to map Moore's law against bloatware.
Right, the bloat of code, okay? And so that's been a big factor. And so as a result, the demand for DRAM has been so high that the cost has stayed high. Whether or not, people have tried to make DRAM be faster, some people have tried. The RAM bus is an example of that sort of thing. But again, if the DRAM has to get bigger, it slows it down too. And so maybe the answer is that performance has improved in DRAM in terms of size, but not in terms of speed. So.
If you're going to buy a computer now, is there some optimal speed you want for the clock?
Oh, that's an easy one. Always buy a processor that's half as fast as the best one that you can buy. Okay, and you'll get a sweet spot in terms of cost. And you won't notice the difference. With the one exception, if you're processing a video file, right, and you're doing a thing like what he's doing there, then you will notice the difference. But most of the other time, you aren't going to notice the difference. And certainly in terms of using the web, it won't make any difference at all, despite what they tell you. The only thing that limits you is the speed of the hookup to the internet, and that's much, much slower than the CPU is. So these days I'd buy 866 megahertz roughly, which is what they sell at the bottom end of the Dell. If you go to the Dell website, just get the lowest speed processor that you can buy. Get lots of RAM. Okay, that'll make it fast. And I'd get 128 meg these days. Next year it'll be 256.
But for the video, you do notice it?
Yeah, and it's a linear thing. If you get a processor that's twice as fast, it'll take half the time to run your file. Now, you may not need that, okay? I'm talking about if you're doing video that you want to edit for a movie or for a television show or something like that. If you're making a smaller size screen, then you don't need such a fast system. So. Okay, thanks guys. See you tomorrow.